Welcome to the fascinating world of wireless concepts. In this realm of technology, we'll explore the magic of connecting devices without the need for physical wires. Wireless technology has revolutionized the way we communicate and stay connected, breaking down barriers and bringing connectivity to even the most remote places. From the convenience of Wi-Fi networks that allow seamless internet access to the freedom of cellular networks that keep us connected on the move, wireless concepts have transformed our lives. Let's explore the role and function of various network components, starting with wireless access points, APs. These magical devices act as bridges, facilitating seamless connections between wireless devices like laptops, smartphones, and tablets, and the wired network. Whether autonomous or controlled by a wireless LAN controller, WLC, APs receive and transmit wireless signals, providing access to the network. For instance, in a cozy coffee shop, an AP is installed to offer free Wi-Fi, enabling customers to connect their devices wirelessly and access the internet with ease. Next, we encounter the Wireless Local Area Network Controller, WLC, a wizardly entity responsible for managing and coordinating multiple APs in a wireless network. With its centralized control, configuration, and monitoring powers, the WLC ensures smooth roaming and optimized network performance. In an enterprise setting, multiple APs scattered across the building are harmoniously managed by the WLC, allowing users to move between coverage areas without losing connectivity. As our journey continues, we encounter the enchanted Access Trunk Ports and Link Aggregation Group, LAG. The access ports create the connections between individual APs and the switch, granting them access to the wired network. Trunk ports, on the other hand, connect the WLC to the switch, carrying multiple VLANs over a single link. Furthermore, the mystical Link Aggregation Group combines multiple physical links between the WLC and switch, increasing bandwidth and providing a safety net of redundancy. Imagine a grand campus network where several APs are gracefully connected to the switch through access ports. The WLC, acting as the wise overseer, connects to the core switch using a trunk port, skillfully managing multiple VLANs. To enhance performance and fortify the network's resilience, LAG is ingeniously configured between the WLC and switch, ensuring a seamless and reliable experience for all users. In this captivating world of network components, wireless access points, wireless LAN controllers, access trunk ports, and LAG form the building blocks that enable the magic of wireless connectivity to flourish. Each component plays a unique role, contributing to the harmonious symphony that is the modern network. Together they create a seamless and enchanting experience, connecting us all in this interconnected digital realm. In the realm of wireless networks, understanding radio frequency, RF fundamentals, is essential for optimizing performance. These networks rely on radio waves to transmit data, and factors like signal strength, interference, and channel selection significantly impact their effectiveness. For instance, in a bustling urban area where multiple Wi-Fi networks coexist, grasping RF fundamentals helps network administrators make informed decisions about channel selection to minimize interference and maintain reliable connections. Wireless networks operate in various frequency bands, such as 2.4 GHz and 5 GHz, each with its pros and cons affecting coverage and throughput. The 2.4 GHz band boasts a longer range, but is more prone to interference due to its widespread usage. On the other hand, the 5 GHz band offers higher data rates and reduced interference, but at the cost of shorter coverage distance. Channel bonding is another technique used to increase available bandwidth by combining adjacent channels. While it can enhance throughput in high-density environments with numerous devices, excessive channel bonding may lead to interference, making it prudent to avoid it in less crowded areas. Modulation and coding schemes govern how data is encoded and decoded over the wireless medium, influencing data rates and reliability. Higher-order modulation schemes like 256 QM enable faster data rates, but demand a stronger signal for a stable connection compared to lower-order schemes like QPSK. In the world of wireless access points, APs, we encounter different types, each with its own unique abilities and applications. Autonomous APs are independent, operating without the need for a wireless LAN controller, WLC. They are suitable for small-scale deployments or scenarios where centralized management is unnecessary. For example, in a small office, a standalone AP can provide wireless connectivity without relying on a WLC, and its settings can be configured individually through its web interface. On the other hand, we have lightweight APs, LUAP, and controller-based architectures. These APs depend on a WLC for central management, making them ideal for larger deployments. The WLC ensures consistent configuration and enables centralized monitoring and troubleshooting. In an enterprise campus, multiple lightweight APs span across floors, guided by the WLC, delivering a reliable wireless experience with consistent settings. We also explore FlexConnect, where APs can switch between local and centralized data forwarding. This feature is beneficial for branch offices or remote locations with limited connectivity to the central WLC. For instance, in a retail chain with remote stores, each store's APs operate in FlexConnect mode, handling most of the traffic locally, reducing the need for excessive bandwidth backhaul to the central WLC. In the realm of mesh networking, APs create wireless links with each other, extending network coverage to areas without wired infrastructure. Mesh networks offer a flexible and scalable solution for challenging deployment scenarios. For example, in a large outdoor venue like a stadium, where running Ethernet cables to every AP would be impractical, mesh APs form a self-healing wireless backhaul, seamlessly connecting the entire venue. In this diverse landscape of wireless APs, each type caters to different environments and needs, providing seamless connectivity for users. Access points, APs, play a crucial role in wireless networks, and their connectivity to switches is essential for seamless data transmission. The link between APs and switches is established through Ethernet cables, with the switch port designated for AP connection, called an access port. For instance, in a school setting, several APs are thoughtfully placed in different classrooms, each connected to a nearby switch, using an access port. This arrangement ensures students and teachers can enjoy wireless connectivity, enhancing their learning experience. When it comes to the connection between the wireless LAN controller, WLC, and the switch, a trunk port is used. This trunk port allows the WLC to efficiently handle traffic from multiple VLANs, corresponding to various wireless SSIDs. In an office building scenario, the WLC is skillfully connected to a core switch using a trunk port. The core switch skillfully carries traffic from multiple VLANs, each associated with different wireless networks, SSIDs, enabling seamless communication for employees and guests. For enhanced performance and network resilience, a link aggregation group, LAG, comes into play. LAG combines multiple physical links between the WLC and switch, providing increased bandwidth and redundancy. In a hospital network deployment, multiple links between the WLC and the distribution switch are configured in a LAG arrangement. This ensures high availability for the wireless network. If one link encounters an issue, the other links continue to provide connectivity, maintaining seamless operations in critical healthcare environments. Telnet and SSH serve as command line-based management protocols that offer secure remote access to access points, APs, and wireless LAN controllers, WLCs. For instance, a skilled network administrator utilizes SSH to troubleshoot configuration issues remotely without the need to be physically present at the AP's location, ensuring efficient and timely resolution. In addition to Telnet and SSH, HTTP and HTTPS serve as web-based management interfaces, allowing administrators to access APs and WLCs through web browsers. By accessing the WLC's management interface over HTTPS, administrators can configure wireless settings, monitor performance, and manage connected APs, all within the convenience of a web browser. Furthermore, the console port on APs and WLCs offers a direct local access point for configuration and troubleshooting. In situations where network connectivity is unavailable, a technician can connect to an AP or WLC using a console cable and terminal emulator software to perform essential configurations. To ensure secure management access, TACAX Plus and Radius authentication protocols come into play. In an enterprise network, TACAX Plus or Radius servers authenticate network administrators before granting access to the APs and WLCs. This centralized authentication and authorization process guarantees that only authorized personnel can manage the wireless infrastructure, adding an extra layer of security to the network management process. Wi-Fi security has evolved over the years, and 3 significant standards have emerged to safeguard wireless networks from potential threats. WPA, Wi-Fi Protected Access, addresses the vulnerabilities found in the older WEP protocol, employing Temporal Key Integrity Protocol, TKIP, for encryption and message integrity check, MIC, to prevent data tampering. For instance, an office adopts WPA to secure its wireless network, ensuring that only authorized users can access sensitive company data. Moving forward, WPA2 takes center stage as the current standard for wireless security. It enhances protection with the Advanced Encryption Standard, AES, offering stronger encryption compared to WPA. In a university campus scenario, WPA2 becomes the chosen guardian for students' and faculty members' data, fortifying the network against potential cyber threats. As technology continues to advance, WPA3 emerges as the latest iteration of Wi-Fi security. This cutting-edge standard provides even greater protection, defending against brute force attacks and offering robust encryption beyond WPA2. In response to the escalating threats to data security, a vigilant financial institution upgrades its wireless infrastructure to WPA3, ensuring the utmost protection for its clients' valuable financial information. From WPA to WPA2 and WPA3, these Wi-Fi security standards act as the guardians of our wireless networks, ensuring a safe and secure digital environment for users and organizations alike. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.